Yeah, record.
Professor,
Hang on.
at the beginning of the class, did you make any announcements?
What announcement you were talking about? Okay, so what is this? 0 to 1.33. Okay. Can you see the table now?
Yes, Professor.
So 1.33. What is this?
0.4.
0.408. This area. 4082. Right, you are. Those who got.
0.408.
Yeah. 0.4082. This is the correct answer. Okay. Question? Anybody got any question?
Professor, why is it 0.9082 I got with the another
It's not
chart?
9, it's 40. What did you say, 9?
It's 0.9082 I got from the another chart.
No, what chart? Do you know how to read that chart?
Yes.
No, you don't. If you knew, you would get the same number. But I don't know which chart is that, so I cannot help you out with that. If you can share that chart with the class, then we can figure out together. Can you share your screen?
Now I cannot, Professor. I just search in the Google and.
In that case, you are making a mistake reading this probability is very reasonable probability. What you are saying is not reasonable. 90% of the values lies between 0 to 1.33 of Z. No, cannot be. You are including the left-hand side area also. That's why you are getting 90%. You should have some sense of Z table. It's just one side of the table. Part of the whole probability is 1. Here is only one part, which is 0.5, and part of 0.5, not even the whole 0.5. So it has to be less than 0.5. It cannot be more than 0.5. You guys don't do mechanically. Think of the values lies within mean. 1 standard deviation, 2 standard deviation. Think about it. Yes.
Can you scroll up?
Scroll up for what?
I wanted to see the Z1. Okay. Fine. That's okay.
You got it?
Professor.
Yes, Professor.
All right.
Professor,
Yes.
I did not understand the last, like in the last class you showed one sum. The last sum I could not understand properly.
The last one.
Yeah, the radar.
The radar.
Yeah.
Okay, radar one. Okay, so what is this? The unit measured speed. Okay, the speeds are normal distributed. Remember, if it's normal distributed, then you can do the Z. If not, then no. A mean of 90 kilometers per hour and a standard deviation of 10. What is the probability that a curve picked at random is traveling at more than 100? So you are looking at the probability where? Huh?
Probability that X is greater than 100.
Exactly. Probability that this is the probability you are looking at, greater than 100. So what you do is you convert this 100 into Z. Okay. So what is Z? Z equals
100 minus 90.
Yeah. 100 minus 90 over standard deviation. Which is
10.
10. So what do you get? 1. So basically what you are looking at is probability that
Value is greater than 1.
greater than 1. So which one, what area you are looking at?
From the right hand side, like after one.
Yeah, let me share it again. You guys have to be very clear about this.
Yeah.
So this table is such that is giving the area between 0 and any value. So that's what you get. Now the rest you find. Okay. So for us it's 0 to 1, but basically we are looking at more than 1. Okay. So 0 to 1 is this. Is it okay?
Yeah.
Huh?
Yes.
0 to 1 is 0.3413. Then more than 1 would be?
This.
Huh?
0.5 minus 0.341.
Yes, exactly. 0.5 minus 0.3413.
But Professor, why I did not understand this part?
Which part?
Like, why are we subtracting 0.5 minus 0.3413? I understood how we got 0.34.
So explain this probability for me. 0.3413.
0.3413 means probability 0, like Z is greater than 0 or less than 1.
So this is the probability that Z lies between 0 and 1. What is the probability that Z is greater than 0?
That is great. 0.5?
Yes. So this whole area is 0.5.
5.
This area is basically this shaded area. Okay.
Yeah.
0 to 1, not 1.96, 1. So
Yeah.
this is 0 to 1.
Yeah.
So then what is the rest of the area? Huh?
Rest of the area is in?
Now, if this is
More
this,
than 1.
yeah,
Professor,
more than 1. Yes.
I'm getting confused because, like, isn't 1 greater than 0.5? So why are we subtracting, like, the value we got for 1 from 0.5? Like, I'm not understanding.
So why? So what did you say first? Which is greater than what?
Like, the number 1 is greater than 0.5, right?
No, 1.5. What did you say? 1.5. This is the value of Z. Z lies between 0 to 1. What is the probability?
Professor, I understood right now. So what we are looking at as, like, we are looking at the probability, not the
Obviously, probability and the values of Z are not same.
Sorry.
Z, the values of Z goes from minus infinity to plus infinity. However, probability lies between
0 minus 0.5 to 0.
probability cannot be negative. Probability always between 0 and 1. Probability can never be negative. What does it mean by negative probability? Huh? Here, remember I said in the first day, what are we measuring on the axis? Z here, X here. These are the values of the variable. But this curve is giving you probability density. Under the curve is probability. This whole area is maximum 1. The whole area is 1. The part of it is 0.5. It's symmetry. This is 0.5. This is 0.5. Okay, I guess you guys are now kind of okay with this, huh?
Yes, Professor.
All right. I'll give. No, I'll get this one. Okay, let's do one more. So make things. Please, everybody, please take your pen and pencil. Okay, pencil and note. Don't sit idle, please. You are harming yourself. You guys are now mature. You are adult. You are going to graduate in a semester. You don't take it easy. This, if you forget everything, this is the course you will have to remember. If you stick to any research, any higher studies, you cannot forget this course. So please, please. Okay, do this. I'll give you 10 minutes. Everybody, please try it. And I'll go randomly ask. Please don't leave the room. Farishta, are you taking the attendance?
Professor, done already. I sent you.
Okay, don't send me. Send to those. Send to the here, yeah, to Saiba. Yeah.
Put it on drive and send it to both.
All right. Yeah. So do it, please. Did you read the question paper? Hello?
Yes,
Yes,
Professor.
Professor.
Okay. Let me look at the table.
Professor, can you go back to the questions?
Done? Hello? Hello? Are you done?
Yes.
Okay. So, once again, Aisha Siddiqa. Aisha. Farzana. Farzana. Jem Noshin. Jem
Professor.
Is it Noshin? Hello?
Yes.
Okay, Noshin. How did you go
Professor,
about
can
it?
you hear me?
Huh? Hello?
Professor, my answer is
Your what?
Professor, my answer is 0.1977.
0.1, what does it mean? Look at the question. Will he be admitted to this university? 0.197. What does it mean? And did you read the question?
Professor, can you show the question again?
Yeah,
Yes, Professor.
yeah. Now you want to see the question again. Okay. Here it is. Huh? Can you see now? Hello?
Yes, Professor.
Yes, Professor.
Yeah. So what is 0.197? What does it mean? Naushin? Can you?
Professor, this is the probability of his score.
This is the probability of what? Let me write. Probability
Tom's score.
that what is the probability? What probability you are reporting?
It should be greater than 70% T score.
Huh? Now, what did you do? You don't know what you did. You did mechanically. You don't know what
Sir, is the probability of his score. Can you hear me? It is the probability of his score.
Yeah, but no, it cannot be one particular score. Is it? What do you mean by one score? Probability of one particular score will be 0. You cannot find just probability of one particular score. It will almost 0. Have we ever done probability of just? So you are saying probability of x equals 585? That's kind of probability you are looking at?
No, Professor.
Huh? No, that would be almost 0.
No.
So what? Okay, now I don't know. Now you don't know even which probability you have found. What did you do in probability statistics class? I'm very worried. Okay, let me ask somebody. Anybody else want to volunteer about this? I guess she got a right number, but she doesn't know how to explain that number.
Professor,
Yeah.
If the area for, let's say, is 0.85 that I find from subtracting of 500 from 585.
Okay. So what you are doing is, let me go one by one. Then you want to know. So what are you doing first?
First, you're going to find Z.
What are you doing here? You are finding the
Z.
You are converting this x score. Is it
Professor,
what you are doing?
I can't hear you clearly,
We are
but
looking for T score. We are going to find T score.
What do you have to see? You have already seen the whole question paper several times. This is the question paper. What do you want to see?
Find the Z score now.
So first what you are doing is you are converting this 585, which John got in the exam, okay, in the test. John got 585. So x equals 585. This
Minus
is the,
500.
what are you doing? You are converting this score into z.
Z score, yeah.
Z is 585 minus
500
500
by 100.
divided by 100, and that gives you
0.85.
okay, 0.85. This is his score in z terms. Okay, his test score is now converted into z score. And now what do you want?
You want to find the probability that
D is
after
greater than
score will
0.85.
be bigger than 585.
No. What do you want now? This question is little bit not straightforward. So, oops. What do you want now? You want the area, the probability that
will get admitted.
Probability that this score, probability that, let's say z is less than this score. Let's say you want to find it, and we will explain why you want to find that. Can you find this score?
Yes, Professor.
Okay.
Yes, Professor.
So let me
It's
go
0.
ahead and share the table. Probability that z less than 0.85. So,
Professor, this is 0.3023.
okay, let's see. 0.85 here.
0.3023.
This part, okay.
3023. Yeah.
Okay, this is the value.
Yeah, I got this point.
This area, this probability. What is the probability? What is the probability? This probability. This is the probability of what?
That is less than the Z score.
1%. So if I give you this number 0.3023, this is a probability, okay, of what? Of Z.
Of Tom getting admitted to the university.
What is the probability that Z lies between? No. Can you explain any number here in the probability area?
0 to 0.85.
0.85.
Exactly. This is the probability that Z lies between 0 and 0.85. Is there anybody who has any doubt about this in this class?
No problem.
No, I guess, I hope. So in that case, this probability is basically 1. I'll write and I'll show you.
Professor,
Yes.
why is it that less than 0.85?
Yeah, that I'll explain why we are looking at this, okay? But first, let's find it, the probabilities, okay? Probability.
Hello, Professor. Are you talking?
I'm not talking. I'm working. Okay, I'm done. So first, you can see this number. Okay, 0.3023. What is this? This is the probability that z lies between 0 and 0.85. Okay, so a part of it, 0 to 0.85 area is given here. However, if you have 0.85 here, what is the probability that z is less than 0.8? How do you find?
Subtract from
Huh?
less than 0.8.
Less than 0.85. So there will be
Plus
two.
0.5.
Yeah, plus 0.5. This area, this one, 0.85. This point, this one plus this whole area. Okay. Probability that z is less than 0.85 is 0.3023 plus this whole area. Everybody agree with that?
Yes.
Yes, Professor.
Hello, others. Because
Yes,
0.3023 is just the area that z lies between 0 and 0.85. Then you have this whole area, which is also less than 0. We are looking at these two areas, 0.5 plus 0.3023. If you have any doubt, you ask me now because I'm switching the screen.
Professor,
Yes.
why is it less than 0.85? Why are we finding Z?
No, that question I'll answer. But first you find whether this is the correct answer for probability that z is less than 0.85. Hello? No, now nobody is speaking.
Yes, Professor.
Yes, Professor.
I hope you understand what's going on in this class. Okay, okay. So if that's the case, let me change the So what I'm saying is probability that z is less than 0.85 is probability that z, so that is the left side from 0 to negative infinity, this area, okay, plus probability that z lies between 0 to 85. So this area is obviously the whole left side, left of the mean, which is 0.5, plus this is the area which is a right hand side shaded area, 0.3023. So you got 0.8023, sorry, 8023. Is it okay? Hello?
Yes, Professor.
Yes, Professor.
So
Yes,
now
Professor.
Now we know that probability that z is less than 0.85 is almost 0.80 something. What is 8033? I guess 23. So this is the probability that z is less than 0.85, which means obviously, probability that x less than what?
0.85.
No, 585. 585 equals 0.8023. Is it true?
Professor, I didn't understand.
What don't you understand? We are going back to x now. You had this x value. 585.
Professor,
Yes.
why are we taking like less than 585 when
No,
in
no,
the
I'm going to answer that question.
okay.
Okay, how many times I'm telling you?
Sorry, Professor.
I'm going to answer that question. But so far, is it right what we are doing?
Yeah.
You had 585 score for John. John's score was 585. We converted that into Z score. And we said that Z is less than that score. The probability is 0.80, which means probability that X is less than 585 is 0.80. Okay, that means 80% of the people scored less than 585. Is that true?
Yes.
80% of the people scored less than John.
Yes.
Yes, Professor.
So will John be admitted?
Yes.
Yes.
Yes. That's why we did this.
Professor,
Yes.
I have a confusion. Like in the question, I can see another number like 70%. So why aren't we using that?
So yeah, but at least 70%. So John had to be higher than 70%.
70%.
John
now
had to
it's 80%.
score higher than 70% of the applicants.
Okay.
John scored what?
It's
80%.
80% more than others.
More than 80% of the students, applicants. So will John be admitted?
Yes.
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 Question. You could do it the other way, from 70% to from that to you could go back.
No, Professor, it's fine. Can you
So-
go a little
Yeah.
down?
So what we did is, okay, John scored. We that score we convert into C, and see what percentile John is on. It looks like John is above 80%. That means he's surely going to get in.
Professor,
Yes.
so like X is equal to 585. So again, why are we taking probability X less than 585?
Less than and equal to, you can say less than equal to. Is it a continuous variable?
Continue? No.
Yeah, it doesn't matter. It doesn't make any difference. So you could say probability that Z is less than equal to 0.85. Okay. If you want to be very correct, you write this. I don't know how to write it, less than equal to in here. So will that change this thing? Huh?
No.
No. Don't worry about that thing too much. If you are very strict, you can do this, but it will be added the same. So question. We are spending too much time on this silly
Can you
thing.
go a little down? I want to see.
What?
Can you go a little down? In this?
Down? Why? What is there in the down? Huh?
There was something. but
Oh, there
I-
is something important. Okay. Here.
yeah.
Yeah, this is what you are looking at. Okay. Always,
can we write it
always
zero?
remember the graph. Yeah. Ask.
So can we write 0 is less or equal to Z, or and 0.85 is also less, or
Yeah. You want to write equal to? Okay. Anything, I don't care. Okay. Anything is better. Mathematicians would object to some. I wouldn't mind. Okay.
Professor,
All right.
I have question.
Will that change these probabilities?
No.
No. Okay.
I have question.
Yes.
Can you explain again, like why is it Z is less than 0.85?
Why Z is less than 0.85?
Like for finding the probability, like why did you find Z is less than 0.85?
Okay. So what we did here, we said X is 585. Okay.
Okay.
So what is X? X is John's score. Okay. We want to know what percentage of people are getting less than this? Let's say only 60% people are getting less than this. Will he be admitted? Huh?
Yes.
No. He has to be above 70%. If his score is like only above 60%, will he be admitted?
No.
Above 70%.
No, above 70% is the condition. The condition is his score has to be above 70%. So if his score is above 70%, will he be admitted? Yes. If his score is above 60%, will he be admitted?
No.
No. If his score is above 90%, will he be admitted?
Yes.
Yes. You have to understand this logic, simple logic here. So we are trying to see whether his score is above 70% or not. Okay. That means we are trying to see what is the area behind to the left. If you know the area to the left, we know to the area right. You could do even greater than x 585. You could do that as well.
Professor, if the score is like at least 70%,
Above 70%. Yeah.
exactly 70%.
Exactly 70% he will be admitted. Why are you worried about that one value? How many values of a normal distribution are there? Huh? How many values? Tell me, how many values a normal distribution can take? Hello?
Hello?
Nobody is speaking.
Yes, Professor. Normal distribution can take minus infinity to infinity.
Huh?
Minus infinity to infinity.
And
Yes.
so you will get exactly 70%. Isn't it very unlikely?
Yeah.
Huh?
Yes.
Yeah, so please don't worry about that. Obviously, if he gets exactly on 70%, he will be admitted because the condition is at least 70%. Obviously, he will be admitted. But the question is, how you find that? So here is the one way we are finding. We are trying to see the area left to that area. What is the area left to that 585? If you see that area left to 585 is more than 70%, that means he is above 70% of the applicants. If to the left area is only say 40%, that means he is above only 40% people. There is no chance for him. If he is above 90%, obviously he is going to get admitted. So could you do it other ways? Yeah, there are other ways you could do. You could see what is the area to the right of X. Could you do that? Huh? What is the area bigger than X 585? How could you do that? Hello? Hello?
Professor, I didn't get your question.
Oh, what did you get? I'm saying what is the probability that X is greater than 585? Couldn't you do that?
From 0.5.
0.5 minus 0.030.
Yeah, what is that value? Let's say you want to do it the other way. Obviously, that's also possible. If you say X greater than or equal to, if you want to say 585, obviously it's equal to. See, that equal to is killing me. You could do that also. That means it would be what? Probability that Z
Greater than equal to 0.85.
0.85. What would be that probability? 0.5 minus Huh? 0.30?
3.
3.
0.197.
0.19?
7.
77. Let's say 8. I think the one who did first, she got this number. Okay.
Yeah.
This also makes sense. It's saying there are only 20% people above his score, isn't it?
Yeah.
Huh?
Yes.
Only 20% people scored more than John. Then the question is, will John be admitted?
Yes.
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 So that way you could also do the same problem. You guys have to be thorough about these things. Okay, I won't spend more time on this silly stuff. If you have any question, you ask now. I'm moving forward. No questions. In that case, I'm gonna shift the screen quickly. So now you have done this normal distribution with some examples and so on. Now there are other distributions as well, okay, which we will be using. A normal distribution is one, and there are other theoretical distributions like chi-squared. You have done chi-squared distribution?
No, Professor.
Don't say no. I guess you did
I
something.
never heard of chi.
Eh?
What is chi-square? I never heard of this.
Okay, chi-square is another. So normal distribution is one distribution, okay? It's a symmetric distribution. Remember normal density function, symmetric,
Yeah.
and goes from negative infinity to plus infinity, and the mean is in the middle and so on.
Yes.
Chi-square is another type of distribution. It's a not symmetric, asymmetric distribution.
And
Asymmetric.
the mean won't be 0 like normal distribution, right?
Huh?
Then the mean won't be 0 like the
No. Who says mean of normal distribution is 0? Did I say that?
in the highest portion, in the middle, in the peak
No,
point.
in the middle. But
Yes.
did I say is 0?
No.
Is 0 only for standardized normal distribution.
Okay.
Okay. Right now you did one problem where mean is what? This Z score, this score, John's score. What was the mean?
585.
585. So it could be anything. But if it's a standardized normal distribution, it's a Z, then mean is 0, variance is 1. Okay. Now there are other types of distributions like one chi-square. Chi-square is not like normal, as a square thing is saying. So when you square, I'll go briefly. Okay. We'll be using them later on. Then if you have questions, you can ask. Chi-square is a distribution. Is basically square of some. If you have a Z distribution, if it's a square of Z, okay. What is a Z? A Z is a normal distribution. Okay. A Z normal distribution with mean 0, variance 1, and you get chi-square by squaring some Z. Don't ask too much here. Just to know that chi-square is a square of Z. So the values goes from where to where?
Minus. Does it make sense? It should be minus infinity to infinity as well.
If you square a minus value, what do you get? You get a minus value?
No. Only
Plus.
So how are you saying that? If you have
Because
a
it's
square, can it be negative?
No.
0 to positive infinity.
Exactly. Now you are thinking in the right direction. Chi-square starts from 0. Chi-square value starts from 0, goes all the way to
Positive infinity.
huh?
Infinity.
Positive infinity.
Positive infinity.
It's not symmetric. It's skewed. It has a long tail to the right. I'll show you a little bit. It has a long tail to the Right. Another distribution is T. T is again ratio of chi-square and F. Okay, let's talk about F first. F is ratio of 2 chi-square. Just to give you some sense. What is an F distribution? F is a ratio of 2 chi-square. Now chi-square is what? Is a squared of Z. F is ratio of 2 chi-squares. So can F be negative?
No.
Can F get negative values?
No.
No.
Because
0 to
if the ratio of positive and positive, you will get all positive values.
Professor,
Yes.
what chi-square denoted as?
Here?
Is denoted
Here? Can you see
Yeah.
this chi-square?
X
Huh?
or K. Is this X or K? It's too
It's
small.
chi,
I cannot-
chi. It's not X or K. It's chi. It's a Greek
Okay.
letter. Here I wrote it C-H-I, chi. It's a Greek letter. You will see it in the list here. If you look at the list here, the symbols, you'll see the chi-square. So chi-square doesn't matter what it denotes. It's by convention it's called chi-square because you are squaring Z. Okay, maybe it's coming from X. And F is a ratio of 2 chi-square, and there is something called degrees of freedom. I'm not going into that right now. So ratio of 2 positive values will give you another positive. So F distribution also goes from where to where? Huh?
0 to infinity.
Yes. T is, however, is a ratio of chi-square and F. Chi-square and F. Let me make sure no, Z and F. T is a ratio of a Z distribution and an F distribution. So what should be the range for T? A Z distribution and an F distribution.
0 to positive infinity.
A Z distribution and F distribution. Ratio of Z and F.
Should be minus infinity to infinity.
Minus infinity to plus infinity. So I'm just giving you just an overview of this. This you should have learned in probability statistics. But anyways, let me show you this, at least the nature of this, the shape of the density function. Okay.
Professor, before you move on, can I ask a question?
Yes, go ahead.
Why did you write students T and F?
No, students T, one distribution. T distribution is a T distribution. Why did I write students T? Now, this student is not you guys. This is the name of a statistician. Okay.
Okay. So, Professor,
who invented T? A guy called student invented T. Okay.
Professor?
Yes.
So F is square of chi-square and T is?
Ratio of 2 chi-square, 2 independent chi-square. I'm gonna quickly go over it again. Okay.
Yes.
So at least basically, you know, if I taught probability statistics for a long time in other years, then these are the things you should learn from there, and these are the distributions, because these are the distributions you will be using in a course like econometrics. You will be using a lot. But we already spent more than 3 weeks on probability statistics. I cannot afford any more. So I'm going to move on to our main econometrics. Yeah, you have questions, you go ahead. I'm trying to find those.
Sir, can you repeat what is T and F?
Yeah, T. So F distribution is another distribution. Obviously, these are all continuous random variables. F you get from the ratio of two chi-square distributions. Okay. All right. So F is always F starting from always 0 up to all the way to positive infinity. Here, so here, can you see this? Which screen I'm sharing now? This one, the book or no? Huh?
No, the doc.
The doc. Okay, let me share the book. Here, chi-square distribution. Okay, the chi-square distribution. If Z1, Z2, these are independent standardized normal variables. Okay. Standardized normal variable. Let's say you have 5, then you square them all and add them, then you get a chi-square. If you have only one Z, you square that, you get a chi-square. If you have 2 Z independent, you add them, you square them, add them, you get a chi-square. Look at this density function of chi. See? When you have only 2Z, let's say from 5Z, let's take it from 5Z, starting from 0, okay? And a long tail here. Take this k equals 5. K equals 5 means you are getting from 5 Z distributions. You are squaring 5 Z distributions, adding them, you are getting, no worries about all those background of the chi-square. Just focus that it's starting from 0 and it's going up quickly and then it gets a long tail. Obviously, it changes its shape with, so chi-square. And then, oh, sorry. Sorry. So I was wrong when I was talking about T. I was wrong means I forgot this. Sorry. So T is what? T is a ratio of a Z distribution and a chi-square distribution. I'm sorry about the ratio I was. Yeah. So T is a ratio of Z and chi-squared, and they have to be independent, and all these, forget about all this, what independence means, and we will just give you a layperson explanation of independence and all this. So T is this ratio, okay, Z and chi-square, and they follows chi-square distribution. Another, yeah.
Can you clarify again the difference between F and T distribution?
Yeah. So I'm doing this T distribution now. What is a T distribution? T distribution is a ratio of Z and chi-square. Okay. In this way, here they are giving you Z. Here is a T distribution. Above here in the numerator is standardized normal. In the denominator, with the square root, is a chi-square with degrees of freedom, which is so-called K. So, what is the range of T? Hello?
Yes, Professor.
The range of T, because Z is from negative infinity to plus infinity, and chi-square is all positive. So, T ranges from minus infinity to plus infinity. Just yes.
Isn't chi-square symbol x square, like the Greek letter x square?
Why are you worried about x?
No,
it's not x, it's chi, and it's a Greek letter. In your book, you'll see that Greek letter.
It looks like x.
Yeah, it looks like that. Maybe it's Greek x, who knows? That's fine.
That's nothing, but
no worries about the symbols. For us, what matters is what kind of density function it has. What is this? For us, only this is what matters. How does it look like? See, it's a T distribution. Doesn't it look like normal distribution?
Yes.
Yeah, T is actually symmetric. T looks more like a Z distribution, but there are differences. T is very symmetric, like normal. So from 0 to the right, what is the area under the density function? Huh? Hello?
Yes, Professor.
What is the area from 0 to right?
0.5.
0.5. 0 to left?
0.5.
0.5. It's a perfectly symmetric. Only that its variance is not 1. Remember, standardized normal variable, what is the variance?
1.
1. For T, variance is more than 1. But T gets actually more and more like normal as this K increases. So lesser sample. If your sample size increases, T becomes more and more like a standardized normal variable. But for a small sample size, T is little bit different than standardized normal variable. If its mean is 0, is symmetric, but its variance is bigger than 1. So that's T. So T is a ratio between a Z and a chi-square, but chi-square is obviously only the positive square root of chi-square. The formula, no worries about formulas. What do we need? These formulas are there. No worries about them. What we need is for you to have a sense of what this distribution looks like, the density function. And there is another one. What did I say? The F distribution. F distribution is, I say, Z1 and Z2 to chi-square. You take the ratio of 2 chi-square. Obviously, there is a so-called degrees of freedom. You get an F. So chi-squares are positive. F will be also positive. Goes from 0 to positive infinity. Asymmetric distribution, not symmetric. Asymmetric distribution. It's a long tail. It's not like Z.
So what about chi-square?
Chi-square is also asymmetric. From 0 to, here is chi-square. Chi-square, I think I talked about chi-square. Yeah, starting from 0 to positive infinity. Okay, this is a chi-square distribution. Here, chi-square variable. So basically, we will be using 3: chi-square, T, F. Chi-square asymmetric, starting from 0 goes up to infinity. F asymmetric, starting from 0 goes to infinity. T, a symmetric distribution, mean is 0, starting from minus infinity to plus infinity. Mean is 0 and variance is a little bit bigger than 1. These all distributions, the density functions will depend on sample size. Please remember this thing. Normal distribution, standardized normal distribution, the density function does not depend on sample size. The distribution depends on only mu and sigma square for normal distribution. Did I say that earlier?
Yes.
Hello.
Yes,
Normal
Professor.
density depends only on 2 parameters, mu and sigma square. But these 3 distributions, their density function will depend on sample size. So the probability under different values will be different depending on what your sample size is. I will not say much about these distributions now. I have some very interesting thing to tell you, which is my favorite, not favorite actually, but they abuse it like hell, so I have to tell you this. Okay, so here, other theoretical distributions such as chi-square, students T and F distribution. So we just gave you a 5-minute overview of these three distributions. Now the very important thing, most important thing of why we do statistics and why statistics is such an important discipline, such an important subject for most of the disciplines. They are using statistics. Why? Because population parameters are usually unknown parameters. So think about normal distribution. What are the parameters there? Hello?
Mu and variance, mean and variance.
Mean and variance. What is mean? Mean is a measure of central
Tendency. Tendency.
Central tendency of a data series. Mean is the measure of central tendency, and variance or standard deviation is a measure of what? Dispersion. So basically, when you have data series, you want to know the mean. You want to know the variance. If you know mean and variance, you know a lot about the variable. For normal, you know everything. If you know mean and variance, you know everything because you know the density function. So you know everything about that variable. Important variables in economics, in other subjects, in public health, in finance. You name anything. You want to know these important things: mean, variance, standard deviation, mean deviation. Also, now the problem is these population parameters, mu, sigma squares, these are not known. If they are not known, what do you do? Hello? If the mean, the variance, they are not known, what do you do?
Have to find out. To find out them.
You do what?
Calculation.
The what? You do what? Say it again. I'm sorry.
Calculation. Summation.
Summation. Summation of what?
Calculation.
Calculation.
Yes.
No, they are not known. You cannot know them. Nobody knows nobody knows the mean. If you have a random variable x, whatever variable that is, the population mean, let's say x is a random variable, normally distributed. Can you know the mean? Can you know the variance of that distribution? That means, can you know mu and can you know variance? Is it possible?
No. No.
It's next to impossible. Even if it's possible, it will be enormously expensive, and mostly they are not known. Nobody knows about really the population mean. I'm talking about population mean. You know how to find the mean of a random variable? Hello?
Yes.
Theoretically speaking, You know how to do that. Expected value. You know how to find expected value. Okay? You know how to find variance. You know the process. But can you know exactly actually what mu is, whether mu is 55 or mu is 99 or mu is 955? No. They are parameters. They are unknown. And that's where this inference statistics is coming to play a role, big role. What do you do if you don't know population parameters, mu and sigma square? Never forget they are population parameters. You are getting them by taking expectation and all this. What do you do? You do sampling. You collect sample. From that population, you collect sample. Now, what is the use of sample? Let's say you are trying to find the you are dealing with the income of this area, Chittagong, income of the teachers. Okay. So, and you want to know the mean income and variance of that distribution. Population one, mu and sigma square. Population mean, population variance or standard deviation. Now that's not possible. You cannot go ask everybody, all the teachers. And what do you do? Huh? Hello?
Yes, Professor.
You go and ask some people, okay? You ask maybe 50 people, 100 people. So that is a sample you are taking. You are collecting a sample. Can you find mean of that sample? Let's say you asked 100 people about their income, okay? 100 teachers. And you find their monthly income. Can you find a mean? Hello?
Yes, Professor.
How do you find the mean?
By the expected mean.
No. So once again, let's say you are trying to find the from population mean, mu, and variance sigma square, which is that possible?
No.
Let's say it's a normal distribution, continuous variable, normal random variable. The mean is not possible to find. Population mean not possible. But what do you do then? You collect a sample, okay? That's what you do when you do research. You collect a sample of 100, let's say 100. So you ask 100 teachers, ask their income, and you noted their income, okay? Can you find a mean income?
No. From population we can't, but if we take certain sample, we can.
Yeah, you have collected a sample. How many people you have asked? 100. And then can you find the mean of that 100 people's income?
Yes, Professor.
How do you find the mean?
The weighted mean?
No, I didn't ask weighted mean. Just a simple mean.
Oh, then summation of x divided by n, which is summation of all income divided by number.
All means how many?
100 people's income
100.
Divided by 100.
100 people's income, you add them, all 100 incomes, divide by 100, you get the
mean.
Sample mean. That is a sample mean. What is that? Do you think this sample mean will be equal to mu?
The sample mean? No, it's equal x bar.
Yeah, so this is, let's say here y is a random variable, okay? What is y? Y is the income of the teachers of this CD. But the mean of y is mu, which nobody knows. What do? You collect a sample of, let's say, 100, and you find the mean, sample mean, y bar. Is y bar equal mu?
No, it's equal to mu, but it's
But
the
what?
sample.
Is sample mean.
Yeah.
So what do you do with that?
We find out the sample income.
You find the what?
Sample mean of the income.
Yeah, you find the sample mean. But what is your goal actually? What do you want to know? Huh?
The mean.
Which
Mean
mean?
value.
Which mean? There are two means now.
Okay, so sample mean.
You sample mean you can find, but what is your goal?
To get a in like.
No, here is the main story of this statistics. Okay, here is the all justification of statistics. I'm not sure whether your professor talked about it or their focus is something else. You basically want to know mu and sigma square. Okay, let's say mu. You basically want to know mu, but that's not possible. What do? You take sample, you find sample mean. Well, then what do you say? You want to say something about mu with the help of sample mean y bar?
Yes.
Huh? That's what all statisticians are doing. They are trying to talk about mu, but they are using sample mean, y bar or x bar. How can they do that? Is that possible? If y is a normal variable, which is normally random variable, which is normally distributed, how many values y can take? Huh? Y can take values from negative infinity to positive infinity. Now you are taking a sample of 100 or 200 or 500, and then you are trying to find a mean, which you are saying sample mean. Okay, and with the help of this sample mean, you are trying to talk about population mean mu.
Yeah.
Huh?
Yes.
Are you making a big mistake?
No. Are you?
How do you know? From millions of values, you have taken just 100, and then you are talking about the mean of the millions of values.
Like it's uncertain. It cannot be accurate. It's not accurate, but
yeah,
it just gives us an idea.
Yeah, what kind of idea? How do you know that that idea is a good one? Have you ever asked that question?
By analyzing the result?
Yeah, the result means y bar. That is the result you got. And you are saying, oh, I got y bar, I got sample mean. Now I can talk about population mean mu. How do you know that that's a good guess about mu? Which nobody knows?
Yeah.
How do you know this y bar is really a good guess about mu? Are you making big mistake? Are you making a little mistake? How do you justify?
You have to find out, research. You have to research and analyze.
How do you analyze? How do you justify your sample mean? That's where actually I don't know, maybe you spend some time on that, but I'm trying to emphasize here before we move on to the econometrics. I'm trying to emphasize here is saying these are called sampling distribution, okay? sampling distribution of sample statistics. One of the statistics is sample mean. Now this sample mean, what do you think? Is it a variable? Is it a constant? What is this? Huh? Hello.
Yes.
A sample mean, let's say y bar. So y is a random variable, let's say with mean, mu and variance sigma square, and you collected a sample which is of 100 or 200 or 50, and you found the y bar. Is y bar a variable? Is it a constant? What is this?
A variable.
It's a variable. How is it a variable?
It's written y is a random variable. That's why.
Why, obviously, y is random variable. It's called a parent distribution. It's a random variable. It is, let's say it's normal. If it's normal, it goes from negative infinity to plus infinity with that density function and all this. How about y bar? Hello.
Can we call it a constant because we find out a certain value?
You got a value. So is that a constant?
Yeah.
So if it's a constant, what is this constant doing with the population mean? What is it telling? Let's say population mean, we mean population mean mu. How do I write mu? I collect it here. I'll get mu from here. Copy. I'll get mu. Mu. So mean mu. This is population mean. I didn't have to write population, but I wanted to. And variance sigma square. Now, really, your focus is here, mean or this mu or variance. Let's not worry about variance right now. Let's say mu. You are really interested to know mu, but which is kind of not possible. Now you have this sample mean y bar. Now you are trying to say from the y bar, you are trying to talk about mu. Are you making a big mistake? What is this y bar? Is it a constant? Is it a variable?
It's a constant.
Is a constant? Then have you done sampling distribution of mean and all this?
Yes.
So if it's a constant, can it have a distribution?
No.
Huh? Can it have a distribution? Means there are more than one values. Okay.
Yeah.
If it's a constant, can it have more than one value?
No.
No. So what is this? Anybody else have any ideas what this sample mean is? What is going on with this? Why we are statisticians are so boastful about talking about many things when they really don't know the population mean or population variance, or for that matter any population parameters?
Professor?
Yes.
Can we call it the subset of the population?
Huh?
Subset of the population.
The what?
Subset.
The offset?
Subset. S-U-B-S-E-T.
A subset. Obviously,
Yeah.
it's a subset. It's only a small subset.
Yeah.
Don't you think so?
Yes.
The population means, let's say, it's a normally distributed population. How many values are there? Huh? A normal distribution, how many values can it take?
Minus infinity to plus
Plus
infinity.
infinity. How many did you take for your sample?
100.
100.
Yeah.
So what do you think? We're taking 100 and you are saying, oh, I know the whole population. I know me, Y bar, which is like, depending on Y bar, you are trying to talk about mu. How can you do that? How can you do that? Hmm? Any other answers on this? Lot of people just left. Don't leave, please. This is an important thing you should know. Actually, yes. Yeah. Time is over, that's why?
No, time.
We still have a couple of minutes, I guess.
2-3 minutes left.
Okay. So, okay. Actually, it's possible if because of this sampling distribution, properties of sampling distribution. Properties of sampling distribution. What is that? If you take the sample, okay, forget about other tidbits, other complications. If you can take a random sample, okay, from equally likely cases, you know, equally likely. So, if you can take a random sample, then even if it's not random, you will have other issues, obviously. So let's say it's a random sample, then this Y bar, this sample mean will be a random variable. If Y is a random variable, a random sample, if you can take, the mean of that random sample will be a random variable. How is it possible? Y bar you said is just a number. How can it be a random variable?
Because we picked randomly and there is no biasness.
Yeah, true, but you got only one number for Y bar. Did you get one number?
Yes.
So how can it be a random variable?
Because we chose randomly, right?
No,
Right.
true, but you got only one number for a Y bar.
But I don't know the answer.
I'm talking about Y bar. These sample mean. How many values did you get for sample mean?
1.
1. Then how can it be a random variable? Have you ever thought of that when you did sampling distribution?
No.
Huh?
Not really.
Okay, I'll leave it there. We'll come back one more class on this, and then we'll move on to the econometrics, our core thing. All right?
Yes, Professor.
Yeah. Okay, you should think about it because the whole econometrics will be based on this knowledge. Okay. Any other questions? If you have, you can shoot now, or I'll call it today.
Professor, can you please answer this question, or else it will keep on rotating in my mind?
No, you think about it because that way you will remember in future. If I tell you this right away, you will forget.
But Professor, it will be very beneficial for me if you answer because I have my HBS exam this weekend. So.
Okay, you enjoy.
Professor, it's related to that also. Can you please answer?
Okay, so very briefly. Now the thing is, theoretically speaking, how many samples can you take? So you have taken one sample of 100. If I go and I take another sample of 100, and if somebody else goes and take another sample, how many samples can be drawn from that population?
Unlimited, right?
With replacement, how many samples can be drawn? Theoretically speaking, not that you are actually taking that many samples, but theoretically speaking, a lot of samples can be drawn from that population. Okay.
Yeah.
So if you take like 500 samples, how many means do you get?
500 means.
500 Y bars.
No.
Theoretically, how many samples you can take? Millions of samples you can take. And how many Y bars you will get?
Like millions of Y bars.
Millions. And then Y bar is it a now constant or a variable?
Variable.
Is now becoming a variable. And if it's a random sampling, it's a random variable. Okay?
Yes.
Yeah, with probability assigned. So, and you will see that Y bar getting one value will have some probability, and so on. So Y bar is becoming a random variable. And then you can talk about that random variable. And theoretically, we will prove that it has some good properties. Okay, good, quote unquote. That's how you can talk about mu even with the help of one Y bar, based on the strong properties of sampling distribution of sampling. All right, that's it for today.
Thank you.
All right, bye-bye.